Now that we have a few elementary differentiation formulas, we would be interested in seeing how those can combine to get other derivatives of other functions. So for example, based on power rule, we can get both of these. The derivative of x to the fifth is 5x to the fourth, and the derivative of cube root of x is 1/3 x to the negative 2/3. It's being x to the power of 2/3. And so what I'm interested in is what happens if based on this, can I do the derivative of 3 times x to the fifth? Based on these two, and how do I do the sum of those two functions? Is that going to work out nice? Their difference. What if I multiply them together? They get their product. What if I divide them and get their quotient, x to the fifth divided by cube root of x? And what about if I compose them? If I take this function x to the fifth and run it through that function. And so it is now this cube rooting action applied to x to the fifth. Now in some of these cases, because of them being powers, we can simplify it, and so we'll know what the answers ought to be. But in general, we're going to want rules for any two functions f and g. This is called the constant multiple rule, because you're multiplying by just a number. This being the product rule, which is a generalization. You can think of this as a constant function times x to the fifth, but generally, if it's not just a constant function and two functions, we're going to need something fancier, which is the product rule. This is the sum rule. This is the difference rule. This is the quotient rule, because you divide things to make a quotient. And then this is composition of functions, but it didn't get called that in history. It's called we call it the chain rule. The idea is that we have this x to the fifth act. You take x, you raise it to the fifth, and then you're chaining that together with the cube root action. So they're functions chained together. We call it composition now, though, so it really should be called the composition rule. But and so the nice thing is that, well, partly nice thing is that these first three, are nice. They work exactly the way you would hope they do. Product rule is not as nice. It has a nice pattern to it, but it's just not do each of them individually like you can with the others. Quotient rule likewise is not as nice, and chain rule is not as nice either. And so we're going to work through these one by one as we take a look at this, and really figure out where they're coming from. So first up is the constant multiple rule. So we've got the derivative of some constant times our function, some number times our function. And the question is, how can I do this in terms of just the derivative of f of x? Well, that would be, if I go through the limit, that's going to be plug in x plus h into that, so that's c times f x plus h minus c times f of x divided by h. But now, well, we've got these two constants there. We can factor out that constant, c times x plus h minus f of x over h. Well, we've got limit laws that say we can pull out the c from the limit, so that's c times that limit. And now the limit that we land with, this here, should look familiar to you. That's just the limit that you use to get f prime of x. And so the way I like to write this, one way this gets written is c times f prime of x. Another way to look at it is c times the derivative of f of x. There's this idea that you can factor out, in some sense, pull out the c from the dx without consequences, without changing the result. Another way to look at it is that you can switch the operations of multiplying a function by c and differentiating that function. And there's a commutativity idea there. But anyway, this is the constant multiple rule. And so, for example, the derivative of 3 times x to the fifth is going to be 3 times the derivative of x to the fifth. So 15 x to the fourth. Pretty much the nicest rule you could hope for. Next up, let's take a look at the sum rule. And so now I've got the derivative of two functions, f of x plus g of x, like the x to the fifth and the cube root of x. If I were to work through that limit, I'll eventually write the formula here. If I do that limit for this compound expression, this adding them together, substitute in all of the x plus h's, and then I subtract all of just the x's, note parentheses, you can put parentheses around there if you want, divided by h. If you work through this algebra, what you're going to see is f of x plus h minus f of x. I'm going to rearrange these, plus g of x plus h minus g of x from the distribution, all over h. But the way the fractions work, all over h is the same thing as this over h plus this over h. And also the way limits work is that instead of doing limit of those two things added together, I can do limits of each individually, assuming the limits exist. All of this assumes that the limit involved that you would do to find the derivative of f of x or g of x exists. If those limits don't exist, what are you bothering to do this for anyway? Well, this is exactly the derivative for f prime of x. It's exactly the derivative for g prime of x. And so there is our sum rule. If we take two functions, add them together, we ought to get f prime of x minus g prime of x. Or, like I did with the last one, you can think of this dx as distributing across. It's not quite what it is, but it looks a heck of a lot like it. And so there is, you can take the derivative and apply it to, you can apply that to that to get that, and dx to g, dx to g. And that's the sum rule. Again, about as nice as you can expect it. It's what you would have guessed it would work as. Last up is the difference rule, at least for this video. This is the difference rule. So now it's just, instead of adding, we're subtracting. And here we can actually cheat a bit. We don't have to go through the limits anymore, because really f of x minus g of x is f of x plus -1 times g of x. And so what we're looking at, we go taking the derivatives of each side, so left more room, by sum rule. I'm looking at that, and by constant multiple rule, I'm really just looking at the derivative of f of x plus -1 times, so just minus dx g of x. And there's our sum difference rule. It looks just like the sum rule, except it's a minus sign instead of a plus. And so f prime of x minus g of x, or again, you can think of it like distributing d of x times f of x minus dx g of x. And so, for example, for our starting example, dx, if I were to take, let's make it a little bit more complicated, 3x to the fifth minus 4 times the cube root of x. If we're trying to do that, well, that's just going to be 3 times the derivative of x to the fifth, which is 5x to the fourth, minus 4 times the derivative of cube root of x. So cut and paste from the beginning of the video. And we're more or less done with our differentiation. Everything else is algebra from here. Just clean this up. 15x to the fourth minus 4/3, and then you can write that, let's say x to the 2/3 in the denominator. That seems clean enough. We'll look at product rule, quotient rule, and the chain rule in future videos.